The previous section introduced the concept of sampling error. A random sample selected from a population will not perfectly match the population. Thus, the sample statistic likely will not equal the population parameter. If this difference arises because the random sample is not a perfect representation of the population, it is called sampling error. Remember that the sample selected is only one of many possible samples that could have been selected from the same population. The sampling error will differ depending on the sample selected. If, in theory, you were to select all possible random samples of a given size and compute the sample means for each one, these means would vary above and below the true population mean. If we graph these values as a histogram, the graph would be a sampling distribution. In this section, we introduce the basic concepts of sampling distributions. Suppose we selected all possible random samples of size 10 from the population and computed all possible sample means. The average of all possible sample means would be equal to the population mean. This concept is expressed as Theorem 1, when the average of all possible values of the sample statistic equals the corresponding parameter, no matter the value of the parameter. We call the statistic an unbiased estimator of the parameter. If all possible random samples of size n are selected from the population, the distribution of possible sample means will have a standard deviation that is equal to the population standard deviation divided by the square root of the sample size. Simply put, as n increases, we would expect to see the standard deviation of the sample mean to decrease, and the distribution of sample means to be shaped more like a normal distribution. If a population is normally distributed with a mean and standard deviation, the sampling distribution of the sample mean, x, is also normally distributed with a sample mean equal to the population mean divided by the square root of the sample size. In Theorem 3, the quantity is the standard deviation of the sampling distribution. Another term that is given to this is the sampling error of x bar, because it is a measure of the standard deviation of the potential sampling error. Notice as the sample size increased, the standard deviation of the sampling distribution is reduced. This means that the potential for extreme sampling error is reduced when the larger sample sizes are used. This figure shows sampling distributions for sample sizes of 5, 10, and 20. However, when the population is normally distributed, the sampling distribution of x will always be normal and centered at the population mean. Only the spread in the distribution will change as the sample size changes. This illustrates a very important statistical concept referred to as consistency. Earlier we defined the statistic as unbiased if the average value of the statistic equals the parameter to be estimated. Theorem 1 asserts that the sample mean is an unbiased estimator of the population mean no matter the value of the parameter. However, just because the statistic is unbiased does not tell us whether the statistic will be close in value to the parameter. But if, as the sample size is increased, we can expect the value of the statistic to become closer to the parameter. Then we say the statistic is a consistent estimator of the parameter. The sampling distribution is composed of all possible sample means of the same size. Half the sample means will lie above the center of the sampling distribution and half will lie below. The relative frequency that a given sample mean is from the center can be determined by standardizing the sampling distribution. As discussed in Chapter 6, a standardized value is determined by converting the value from its original units into a z-score, or a z-value. A z-value measures the number of standard deviations a value is from the mean. This same concept can be used when working with a sampling distribution. Note, if the sample being selected is large relative to the size of the population, or if the sampling is being done without replacement, we need to modify how we compute the standard deviation of distribution and z-value using what is known as the finite population correction factor. The finite population correction factor is used to calculate the standard deviation of the sampling distribution when the sampling is performed without replacement or when the sample size is greater than 5% of the population. In this example, the mean for the population is 1.5 with a standard deviation of 0.05. We've been given a random of 8 values. We have a sample mean of 1.565. After defining the sampling distribution for the sample mean using Theorem 3, we have a sample average of 1.50 and a standard error of 0.0177. So in this case, we're interested in the probability of x bar being greater than or equal to 1.565. So we'll convert the sample mean to a standardized value using our z-score formula, and the corresponding z-score is 3.67. Thinking back to the empirical rule, we know that being 3.67 standard deviations above the mean is going to put us in a low probability region, so approximately 0. Theorem 3 applies when the population is normally distributed. Although there are many situations in business in which this will be the case, there are also many situations in which the population is not normal. For example, incomes in a region tend to be right skewed. Some distributions, such as people's weight, are bimodal, a peak weight of group for males and another peak weight group for females. What does the sampling distribution of x look like when the population is not normally distributed? The answer is it depends. It depends on the shape of the population and the sample size being selected. The central limit theorem is very important because with it, we know the shape of the sampling distribution even though we may not know the shape of the population distribution. Here we can see how a uniform population distribution becomes more normal as we shift from population to n equals 2 and n equals 5. In this slide we have a triangular distribution for the population and a sample becoming more normal at n equals 5 and n equals 30. And finally, we're also able to see the same result when we deal with skewed population distributions. The catch with the central limit theorem is that the sample size must be sufficiently large. So what is sufficiently large sample size? The answer depends on the shape of the population. If the population is quite symmetric, then sample sizes as small as 2 or 3 can provide a normally distributed sampling distribution. If the population is highly skewed or otherwise irregularly shaped, the required sample size must be larger. Simulation studies indicate that even in a very strange looking population, samples of 25 to 30 produce sampling distributions that are approximately normal. A conservative definition of a sufficiently large sample size is n greater than or equal to 30. Go ahead and open Excel file CEO compensation and answer the following questions. I'm going to start by using the descriptive statistics function in the data analysis package. So that's our summary for the population. We can see the mean compensation for the population of CEOs is about 27 million with a standard deviation of around 13 million. It's definitely good to be a CEO. Alright, so now we want to find a simple random sample of 30 Of course, let's find the average of this sample. So we can see the sample mean of about 25 million is less than the population mean of 27 million. So now we want to find the probability of getting a sample mean as extreme or more extreme than the one we just got. Since our sample is large relative to the population, we're going to need to use the finite correction factor. So now let's standardize our values. So now we want to find the probability z greater than or equal to negative 1.16. And because we're looking at greater than or equal to, we'll do a 1 minus. So we see a high probability of getting a sample mean as extreme or more extreme than the one we got.